All right, welcome to episode 2 of how to become a data-driven enterprise with AI. And today's focus would be the basics of machine learning model building. Okay, uh, just to recap of what we have talked about in the previous episodes. We talked about since the previous episode was the starting one. We talked about the organization of the webinar series and outline and everything. And we talked about what a data-driven enterprise is and what kind of role AI can play in those organizations. And then we talked about some terminologies, some widely used terminologies such as AI versus machine learning versus deep learning versus data science. And then we talked about the basics of ML at a very high level. So we talked about supervised and unsupervised learning, and we talked about the supervised and unsupervised learnings supervised learnings are usually of two types based on the output. So that if your output variable is continuous, then we call this type of problems regression problems. If it's a discrete, then we call it classification problems. And we talked about unsupervised learning also, and most of the times we use clustering type of things for those. We went over some code examples. Okay. So for the agenda for this episode is taking a deep dive into supervised learning models. Basically, we'll talk about regression and classification. Will just do a recap of what we learned in the last episode about this too, and then we go into deeper model building basics, right? So we talk about how do we take data and then break it into train, test, split, so that we can ensure a good performance on unseen data. Then we'll talk about we'll go deeper into machine learning model buildings. Okay, we start with a regression example, and we talk about model fitting and some techniques related to overfitting and underfitting and bias-variance and other things. All right, and then we'll also show some code examples towards the end. So again, as I said, just to recap from the last episode, that supervised machine learning is a type of machine learning where a label data or tag data, okay, of the outcome variable is provided. So again, please recall that outcome variable is the output, right? That's how we call it. Or inputs are either called features or input variables or predictors, right? Okay. So in this scenario, okay, your input would look like X and Y, right? So basically X would be the feature values, right? And then Y would be the outcome variables. And as I said, depending on if it's discrete, then we call it the classification problem. So that will be the focus in our next episode. Today's episode will be mostly looking into a simpler kind of problems, which is regression. Okay, so where the problem is continuous. Okay, and today we'll mostly focus on linear regression. We'll go into the depth of linear regression and see how this type of problems are set up and then solved. Okay. So at the heart of any machine learning problem, right? When you're building a machine learning problem, what we try to achieve, right? So why are you building a machine learning model? So in a machine learning model, what happens is that we are given some training data, what we call the available data or training data, and in a supervised setting, that has to be labeled. Okay, that comes at a cost also. And our main model is to take this small fraction of this training data and to build a model there. So, and then we'll come to we'll talk about the definition of what a model means, okay, and so on and so forth. But one of the biggest thing that we try to achieve there is what we call generalization, meaning that we are building our model on the training data, but with the goal in mind that it has to work perfectly, or like very good in unseen data, right? So if that we cannot achieve that, then our approach has failed, right? So our goal has to be we need to make sure that the unknown data, that is the data outside the training, the small training data that we have, our model should perform better there. And to ensure good generalization, what we do is that we try to mimic this process, meaning that we take this data with the available data, and then we further split into a training and test data set. Okay, so basically, and then we build our model, and then we try apply it on the test data set just to mimic that unseen data part. Okay, so this diagram shows here what usually is done in practice is that we start with the available data, and we separate it into a train and test split. Usually it depends on how much data you have and some other discretions, but usually like in widely used practices to take 80% of the data for training and 20% rest of the 20% for test. So one important thing to keep in mind is that this test data set, you must make sure that this is not seen by the model or your algorithm during the learning process at all. So this, you can think of it as like it's kept aside or locked in a log box. Okay, we also call it a holdout data set, meaning that the model must not see this. Okay, so think of it this as the analogy of when we prepare for a test, right? When you learn something and prepare for a test, right? So the test questions or the test the exam, right? That's sort of like the test data set that must be kept aside, and then we must prepare ourselves so that we can do well in the unknown test, right? And what we do with the training data is that sometimes in the model, we need to tune a lot of things. We'll talk about those later, things such as hyperparameters. So we'll talk about what a parameter is later on, but hyperparameters are sort of certain aspects of the model itself, right? So sometimes we need to tune those. You have probably heard about neural networks, right? So hyperparameter neural networks could be the number of how many layers you are going to put, or what type of algorithm, what type of learning algorithm are you going to use, meaning that what type of optimization are you going to use, those type of things. So to tune those, we need to further separate out the training data set into a train and validation sets. Okay. Now let's talk about what do we understand by model. So far we've been talking about models, but what is a model and how is it different from algorithms? So we hear these terms, machine learning models versus machine learning algorithms, right? So they are very related, but one thing is that the algorithm, when you say algorithm, it's actually we're talking about a particular method, such as linear regression algorithm or deep learning algorithm or tree-based algorithm, right? And when you say model is actually the result or the programmatic output of this applying this algorithm, right? And we often represent the input-output relationship that we talked about, right? In the supervised learning, we are given some input feature X and some labels Y. What we try to learn there is that we say that, okay, there is a relationship between X and Y in the sense that Y is a function of X. So that unknown function is what we call model. So for the same given training data, you can fit it as a logistic regression model, you can fit it as a training tree-based model, you can fit it as a neural network model. So those, the X and Y remain the same, but your F is changing. So that F, or the functional relationship, is what we call models. Okay? And one of the things that you'll encounter is that these models can sometimes be parametric, or sometimes they may be non-parametric. So we will take an example of linear regression today. We'll take a deep dive into that. And that's an example of a parametric model. So basically, a parametric model is a model where it uses a set of parameters to represent the model. Okay. the coefficients in a linear regression or logistic regression or weights in neural networks are parameters. So in a parametric model, what we do is that we may have, let's say, millions of training data points, but we may use only a small set of parameters to represent this data. And once the training is done, okay, then the model is nothing but those learned parameters. Okay, so we'll take a look at these examples. And then we can throw away the training data completely because we don't need that. Those parameters that we have trained represents the model. A sorry, it's a typo here. It's a non-parametric model. I'll fix it later. Non-parametric model doesn't explicitly use any coefficients or parameters, such as k-nearest neighbor models. Okay. So in k-nearest neighbor model, we don't build any models or we don't use any parameters. So the entire data set is used. So we'll talk about it when the time comes. So as I said, again, one of the simplest algorithm to understand and to go deep into is the linear regression model, which is an example of supervised machine learning model. Although it may sound very simple, but it's widely used in the industry for a variety of problems. Okay, so what do we do in linear regression? In linear regression, in the last episode, we have worked on from a very high level, we worked on a problem of, let's say, housing data. So basically, there are some inputs given to you, some features of a housing, right? What is the location, zip code? What is the number of bedrooms, number of bathrooms, and so on, and some other factors about the school districts and others, and then a house price is given. So basically, given this numeric variables x and independent variable y is the house price here, our goal is in the linear regression is to find a model that is, so the model for linear regression is like represented as y equal to beta 0 plus beta 1 x plus beta nx. So here, basically what we are doing is that for each of these parameters, each of these input variables, we have a coefficient beta, right? So for input feature x1, we have beta. Input feature x2, we have beta 2. Input feature xn, we have beta n, and then a beta 0, which is a bias term that's also used. Okay, and our goal in linear regression is to learn. So we are given x's and y's. Our goal is to learn the betas. Okay, and if you relate it back to the parametric models that we have talked about, so these betas are the parameters here, right? And here, these parameters is what you retain after your model is trained. Okay. So in a linear regression, the question might be then how do we learn these betas? So our goal would be to learn these betas. So here I show you a very simple example of this is called a simple linear regression where we have only one-dimensional data point. So we have only x and then there is y, right? So there are some data points here provided for you, and our goal is to then learn. So first of all, think this red line that I have here, it does not exist. So these data points are provided for you, and then our goal is to learn this this line here. Okay, and the way we learn this is by first finding, okay, that if this line hat, as we have called here, then for any data point on y hat here, as you can see the red point here, okay, so for this input xi, there is this this is the label that's given. There is the supervised label that for some feature x, this is the output. Okay, and then if this is our model's prediction, then we are making an error here, right? So ei is the difference between them. So in linear regression, what we do is that we use a loss function. So we will see later on that this is the heart of any machine learning algorithm, is that you are given some input data, you have created a model, then you try to find the loss function between them, meaning what is the difference between them, or in any other way we define a loss function. So here in linear regression, the loss is defined as something called the sum of squared error, or SSE, or we can call the loss. So this is, as you can see, that this loss can be positive if you say that this is the difference between y hat and yi here. In this line, it is positive, but in this line it is negative, right? And so on. So we cannot just add them up straight, then they will cancel each other. So what we do is that we take the square of this, which is like sort of uh, 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 sign independent, so it doesn't depend on the whether it's positive or negative, and then we add them up. So basically, uh, uh, our goal is to then find a solution of beta, right, that minimizes this sum, right? So this loss function, that is actually if we replace y hat, which is beta 0 plus beta 1x, because we have only one variable here, this becomes the sum of beta 0 plus beta 1x minus yi, which is our input. So basically, this is our model's prediction, right, for this point, which is this y hat, the red point, and the difference between what actual value is. And then we just add them up and solve it, right? So we will see in the programming example is that that when we can use Python package scikit-learn for fitting a linear regression model by creating a linear regression object and giving it the x and y's. Okay, so you can see that these are the x and y's, the inputs and output, input and input features, and the output target variable. And then we said dot fit. Okay, so this is a very important concept. You will use if you use scikit-learn, which is Python's very popular package for machine learning. This model.fit, regression.fit, or tree.fit, this interface remains the same. So basically, if you use scikit-learn to build any model, you'll be always using this dot fit. Now, you may always wonder that what happens when you say something dot fit, right? When you fit a model, what's going on? Basically, a model fitting, when you say a model dot fit, that's the model is taking the x's and y's and it has an optimization algorithm. Here you could use something like for linear regression, there are like some we call it closed form solutions that are available. But if your loss function is complicated, then we use something called gradient descent algorithm, optimization algorithm, that we will see in our future episodes, especially when we talk about neural networks and other complex models. So basically, the dot fit is then going over all of our training examples. So this is very important. Please, to see like how the model is being trained. So it goes over, the algorithm goes over each and every training point provided, and then it actually tries to find the loss function for this, and then it tries to walk through the loss function space and finds a point where a certain value of the beta that minimizes this particular solution, right? The particular loss function, and that is called fitting. Okay, that is called model fitting. Now, as we do, we fit models. Okay, so some things can go wrong, and we'll talk about those in details today. So, as we said, at the beginning, the most desired property of machine learning model building is generalization. Okay, so that the fitted model can work with unseen data. Okay, and then for that reason, we do train, test, split, and everything. But most often models fail to achieve a good fit. Okay, and that happens because we either suffer from a problem called overfitting or underfitting. And two related terms for this are bias and variance. Okay, so an overfitting happens when we make our model too complicated. So the analogy of that is, again, let's say you are preparing for a test and you are studying. Okay, so if you don't try to understand the topic and try to memorize it very well, so you have a very good capacity of memorization, so you memorize everything. So that is called overfitting, meaning that then you are not expected to do very well if in the test the problems are different or something not related to what you have seen in training. So if you try to memorize, then if it's outside of your memorization, then you will not do well. On the other hand, underfitting is something that you did not learn the process very well. So we try to find a balance between these two. Okay. So for this part of the discussion, I'll switch to a whiteboard to illustrate the concepts. Okay, so let me just switch to this. Just give me 1 second. Okay, so let's go this and let's start from here. So what we have learned so far is okay, so we are talking about linear regression, right? So basically we have this x and this y, and if we are given some data points like this, right? So our goal is to then fit a model here. So so what is a model bias? So basically, if we look at this data and say that, oh, I think that we can fit a line here. Okay, so we can fit a line here, or let me just take it, change the color here. Okay. So as soon as we say that, okay, so there is a line, maybe this is a linear relationship. We are adding a bias. Okay, this is called the model selection bias into this algorithm, right? So the simplest model that you can think of can be a line or a constant line, but we can make it also very complicated, right? So instead of this, we can have a quadratic model, so which is like this, right? That can fit this model. So there are lots of model choices, and in the extreme, we can fit a model that goes to every data point. So what happens with this type of model is this model, we call it, has low bias because we are letting we are fitting our point through everything so that our training would be very good, right? But for this type of problems, what will happen is that since this is similar to memorization, right? In this case, the performance on test data set will be very bad because you can see that it actually has gone through everything, right? On the other hand, if we make it really, really simple, right? So for example, let's say just a constant line, right? Then this represents something called high bias, meaning that we are actually using a very simple algorithm. The definitions of bias and variance you can check out, but this is the crux of the idea, is that if we use a very simplistic algorithm, then our models are at this point we call underfitting, right? Underfitting, as opposed to going over everything, which is the other extreme. That's where we call the model is overfitting, right? So this is an overfitted model, and we try to avoid both, and we try to find a balance between them. So basically, what happens in overfitting and underfitting is that basically, if you're training your model, right, as your if this is number of iterations of the model, number of iterations, and if this is the error, so it could be number of iterations and or the complexity of the model. You can take it in both ways. So what our goal is that as we are training the model, as you're giving more and more data, the error should come down. So this is the expectation, right? This is on the training data set, right? So the training data set, we want our algorithm to learn. So this is the training error, right? Then it should come down. And there is another concept, since we do a train test split, our test errors are also should follow this, right? In an ideal scenario. So this is an ideal scenario, and usually test errors are usually a little bit higher than the training errors. So this is the ideal scenario, and this is the gap that we call the generalization gap. So the gap between these two. But what happens in an overfitted scenario is that your model would perform very well in training. So training data would be very good, but in the test cases, what will happen is that it shows a behavior like this. It goes down, and then suddenly at some point it starts going up, right? So at this point, we say that the model started overfitting, okay? Because at this point, that the performance or the generalization gap is very high. Okay, so we want to avoid this type of scenario. Okay, so that's in the sorry, we don't have much time. So in short, that is the concept of bias and variance, and this comes as a trade-off. And let me share my screen again. Is my screen visible?
Yes.
Okay. So again, in a bias variance scenario, okay, we didn't talk about the variance part. Sorry, variance is where we see that when we have an overfitted scenario, our models are prone to small changes in the input. So right, when you overfit too much, right, your model has to use very high values of the coefficient so that any little change actually results in completely different output. And that's why our test set performance is very bad and it doesn't generalize. Okay, so this is what the two errors, right? In a high bias, low variance scenario, the top part, where both of the errors are very high, we want to avoid that, right? And that's the part we call underfitting, right? And to the other extreme, where our model training error is very, very low, right? The training error in the lower right corner, you can see the training error is very low, but our test error is very high. So always remember that our goal is to not fit a very good training model, because for the generalization principle, we need to make sure that we have a very good performance in our unseen data. Okay, and we often try to find a combination of sort of a trade-off between these two. And you can see this is the definition of bad generalization, where we see this type of situation happening in mostly in deep learning and in other processes where we have a very good performance in training, but our test performance is very bad. So this type of situation must be avoided. Okay, and how do we solve this type of problem? So overfitting is one of the most serious problems in model fitting. So it gives you an idea that, oh, you have a very good model, right? Because your performance on your training data is very good. But in fact, you don't, because when you take it to production, or when you're applying this in your enterprise, right, then all of your algorithms perform a very poor performance, right? So they perform very poorly. So we want to avoid this situation. So for this, we use something called regularization or cross-validation to make sure that our model is not just fitting some noise, right? So in overfitting situation, that's what happens. So we want to make sure that it's not fitting noise in the data set, rather it's performing overall, it's performing better. So if the situation is the bottom line here, which is before regularization, and before regularization, you can see the generalization gap is very high. It's the difference between the top and the bottom. We can use something called L1 or L2 regularization, which we'll probably cover later on. Is that we try to then make sure the model actually, we don't want such an extreme like performance. We want to make it a little bit, the training process a little harder, and such that it does not use all of its capacity. Okay, so when you give it more capacity or more complexity, then the model actually tend to start to memorize. So example of a capacity would be the example that I showed in the whiteboard, is that you have some data points and you try to fit, go through every points in this, meaning that you are using a n degree polynomial where you could just fit a line on this one, right? So those type of situation you can avoid. And then for that, we could use L2 and L1 regularizers as a solution. Okay, so I have some coding examples that I'd like to show here. So basically, I will share as we did all this. So we'll share this notebooks with you, and here we have taken a deep dive into a linear regression. Basically, here is the thing. So we first talked about trend test split and linear regression and the bias variance trade-off that we talked about. So basically, for this we used a diabetes data set. So it's very simple. So let's first get this, and then you can. So this data set, the diabetes data set, it gives you some features, and this is a data set ready for regression type analysis. It probably outputs the blood glucose level of a patient. And we have first, what we are doing is that we're loading this data set. This is part of scikit-learn, so you don't have to load any data set. So you could just say load. It comes preloaded in this, and then we are splitting them into train and test. Okay, and to keep it simple, although this data set has 10 features, we are using only one feature, okay, to build this. So basically, after this, it's only one dimensional, although the original data is actually 10 dimensional. Okay, so then we build a regression model on this. So basically, we're telling that given this train, okay, build a model, and then give us the prediction, and then we plotted our prediction on our test data set. So basically, this is what it looks like. So our model, so the red line is our model linear regression model. So in a linear regression of one-dimensional case is nothing but line that we are learning. So it's basically there are two parameters, the beta 0 and beta 1 is sort of like the, if you remember from your high school math, that y for equation of a line is y equal to mx plus c. Here beta 0 and beta 1 are, C is the beta 0 and beta 1 is the M. So basically it's learning those two. So from the training, it's learned the red one. And then we are seeing that in the test data set, it's performing okay. It's not that great because it's making some errors, and that will be the case. The errors, there will be some errors. You cannot fit linear regression model to 100% to be 100% accurate in anything, because this comes with a lot of uncertainty. And I have shown a more complex problem. So using the previous Boston data, okay, we loaded it, and then we actually created a prediction model. Okay, and then so this Boston data set is 11 dimensional data, and you can see that this is what we get as a model output. Basically, this is what so once the Boston data set might have 10,000 data points, but once the training is done, this is the model. Again, this is the model. So this has 11 coefficients, or so if you have features is n, there will be n plus 1, because there is one bias. And then this has, after the fitting, the mean squared error is, so it minimized it to 24.29. Okay, and so this also tells something called R square value, like how good is the fit. As we like it to be as close to 1 as possible. So this is like a kind of an okay type of fit. Okay, then we have explored this bias variance trade-off in model building. So for this, this is very interesting. You'll see that what we have done is that we have created a data set. We have drawn a data set from something called from a sine function, right? So to generate some random data, something like this, and we did a train test split on this. And on the training data, as you can see, the red points of the training data. Here, again, we have the similar type of problems that we have seen in the whiteboard, is that we have a choice of fitting different types of model. We can fit a line, we can fit a 2-degree polynomial, 3-degree, up to the possibilities up to 100 degrees, because there are 100 data points in the training data set, or 80 data points. We can feed up to those things, right? So as you see that we are running a complex model here. I mean, if you go to the plot, there are a lot of these things. But what we're doing here is that we are fitting 10 models with starting from degree 1 through 10, and for each of them, we are calculating the errors and training and test errors and plotting them. So this is just an illustration here. It shows that in the data set, right, as you are increasing the complexity of the model, right, your train test is going down. So your train test is doing very good. As you go to 10th degree polynomial, your training error is like very low, it's 0.87, okay, as opposed to the second, so 2-degree polynomial, which is 1.05. So basically, obviously, we would like to think that this is our best model, 10-degree polynomial. But if you go into our test data set, we'll see that it is not the case. And actually, the 2-degree polynomial is the best one here. And you can see that the test error is very like is getting higher and higher. So this is an illustration to show you the concepts of bias and variance. I think that I'm a little over time today, but please explore this. This is really interesting. And I have left some exploration idea for you. So to use the regression model on diabetes data set using all variables, I've shown it for one, and then try to see if you can apply regularization on this problem and see how it behaves. Okay, so I will stop here and then take any questions you might have. Any question from the audience? So I think you guys are feeling shy. So if you have any questions, please use our Slack channel to like ask us any questions. I'd be happy to answer. I know that yeah, so these are probably a little bit of information overload for everybody, but these are the basic concepts. And I think when you're building your career as a machine learning professional or AI professional, so these are the things you have to keep in your mind, right? So if you had to take away one takeaway from this whole conversation is that when you build our models, we need to be very careful about when you're fitting it. We should not be very excited by seeing the training error coming to a very coming to a low training error, right? So basically, that doesn't tell us that how it's going to perform in the test data set. So we need to do a very good like train test split and then apply and then make sure that we have sort of a reasonable performance in the test data set as well. So this overfitting scenario is actually one of the most common problems you will encounter in practice. So this gives you sort of a sense of a false positive, meaning that you think that you have a very good model, but in practice you don't, right? So you want to make sure that that instead of going for a, let's say, 0% error, we should try to make the error a little higher if needed, but make sure that it does very well. So I have a question here: can you calculate bias, variance, and irreducible errors separately, or these are just notion? No, of course we can calculate the bias and variance and the other error. Basically, if you guys have just a few seconds, I can show you maybe in my slide here. So here, going back to this problem. Okay, so bias, if you're given, let's say, a set of data points, right? So think of bias as like this. So let's say this is your target data point, and you're trying to make some predictions, right, of the target. So your prediction, so if this is your actual, let's say, y, right, and you're making some predictions, y hat, right? So let's say your predictions are all over here. So if this is your y hats, right? So then the expectation of all these values, meaning the average of all these values, okay, and the difference between that and your actual value. So this difference is called the bias. Okay, you got it? So basically, if your target is here, then we like our, so a reasonable thing would be to make our predictions which falls very close to it. So if the predictions fall here, right? Again, this is our actual value that we are trying to predict, and this is this. So the average of this is here. So in this case, the bias is just this. So bias is very low. Okay, and the variance is the variance of this data point. So basically, if your data point is very scattered, again, I'll take another example. So if this is your true example, and if your model predicts these values, let's say here, right? Then this model's average would be probably, this is the average. So this model, can you guys tell what is the bias here? So the bias is the average of these models, this, okay, and the difference between this. So this is the bias. The bias is low, but since this data set is very, these predictions are very widely sparse, right? So the variance should be high. So variance is high here, right? So, and one analogy for this you can take is that, let's say this is a bullseye, right? Meaning there's a target. I give you 4 scenarios of this target, and you're throwing, you're trying to hit the target by throwing some darts. Dart means like some arrows, right? So if your arrows fall here, but they are close to each other, then we have a, and the bias is this, right? So we have a, let's call it high bias and low variance, right? Because the variance is low. If your targets now fall here, and let's say your targets are now here, right, around this, the average is here. So here, what do we have? Anyone? We have a low, sorry, let me take a better color here. We have a low bias because the bias is low here. Our average of the estimates is very close to our actual value, but the variance of the estimates is very high. So high variance, right? So this is the one that is the actually scenario of that we try to avoid also. And then we try to avoid high bias, low variance. So the ideal case should be very similar, something like this, meaning that so this is where our low bias and low variance, right? And the situation like this is the worst, right? So this has what? The bias is also high here, right? The bias is high. Yeah, the bias is very low. So this is high bias and of course high variance. Okay, does that answer your question, Amar?
Yes, thank you, Badrul.
All right.
Okay, so in this, for one particular point, we can answer this way, but as a whole, when we train the model, can we calculate that for all points, what is the total bias and what is the total variance?
Right, right. So as I said, right, so the
trained model.
Right. So this would be if your actual parameter, actual estimate is y, right? This would be y minus expectation of y hats. So that, and then I think they do a square. I don't remember the difference, but this type of, so this is the all of your measurement, all of your predictions, average, right? And then what is the true value of that? So that will be the bias. And variance is very simple, right? Variance we all know, like all the estimates, is the variance of the estimates. Okay. Yeah. And
okay, thank you.
Yeah. Okay. Any other questions from anyone?
Yes.
So am I sharing still? Okay. Any questions from anyone before we close? So yeah, so first of all, thank you very much for joining this second episode. Yeah, I hope you learned some basic concepts of model building, and please do let us know if you have any questions. Thanks. Bye.